Dr. Ravi Pawar sir as our today's session invited speaker. Dr. Ravi Pawar sir is currently working in Indian Institute of Technology, BHU, Varanasi. Sir has completed PhD from IIT Roorkee and postdoctorate under Brain Korean Research Fellowship at South Korea. Dr. Pawar sir is active and senior member of various societies and has published more than 80 research papers in reputed journals, published many book chapters and conference papers also. Sir's area of interest and has notable contribution in the field of microwave absorption, metamaterials, frequency selective surfaces, application of AI and ML in electromagnetics, terahertz material devices and electronic waste management, and many more in a row. Good morning, Dr. Pawar sir. Sir, on behalf of EICT Academy MNIT Jaipur and Department of Electronics and Communication Engineering MNIT, we welcome you all in the today's session as invited speaker. Request you to, sir,
Thank
kindly
you.
take over the session, sir.
Yeah, thank you. Thank you very much, Swati, for the introduction.
Pleasure, sir.
I hope my slides are visible now.
Yes, sir, your slides are visible.
Yeah, thank you. Thank you so much. So, first of all, uh, thank you, Swati, and thank you, organizers, for inviting me for this session and to present a key research activity ongoing in my lab. One of the research activities going in my lab in front of you, where we are using the e-waste for some radar absorption applications. And since the theme of the workshop is also frequency selective surfaces, which is also one of the important part of the stealth technology. So I would like to present some of the key research activities where you will see that how the e-waste can be utilized for the radar wave absorption, in turn also in the development of frequency selective surfaces also, which are a new kind of frequency selective surfaces. So this is first of all just a overview of our city Kashi, Varanasi, which is well known for its spirituality, for its cultural value. These are the just a few glimpses of our city, where you will say, which is well known for the Lord Vishwanath and its ghats. And in this beautiful city, we have this institute, IIT BHU, which is, I would like to say, a capital of knowledge, which is an only IIT in India, where we are sharing a campus with a prestigious university, Banaras Hindu University BHU, and that's so called. It's an IIT BHU. And these are the few images of our institutes, which clearly show our old heritage, as well as institute also having a very beautiful temple in the campus. You can see one image here in the picture itself. And this is the now come to my research lab. So our research lab is interdisciplinary in the nature, and we have people from different background, like we have people from science background, also from engineering background, also we have people from electronics engineering, electrical engineering, mechanical engineering. We have also people from physics background and from chemistry background. So our research team is too interdisciplinary, and these are the few research activities which are currently ongoing in my lab in that series. So first is the stealth technology, which we will discuss today. We are also working on EMI shielding techniques. We are also working on antenna and radome technology, waste management, which is also theme of the today's talk. And specifically, we are working on various waste stream, but one of the very important waste stream is the electronic waste, where we are working in, and metamaterials and frequency selective surfaces, which are a kind of artificial materials, we can say that, certain kind of periodic surfaces. And we are working on nano composites also. So my research group is working on the interface of all these techniques, and these are the major outlines of today talk. So brief introduction and background, what are the key challenges, and what are the current technology and trends are there in this area, and followed by the concluding remarks. So let me start with the electronic waste. So first of all, you need to understand what is the waste. So it will achieve its whole lifetime, any product or anything like that, and it is of no use. So you can take an example of your mobile phone also. Means after 2 year or 2.5 year or 3 year maximum, your mobile phone or your other kind of electronic gadgets are of no use generally. So we call them basically waste when they are of no use. And this waste can be your medical waste, this can be your electronic waste, this can be your agriculture waste. all other kind of waste stream can be taken care of, but one kind of the waste stream which is increasing day by day, that is the electronic waste, and the waste which is coming from the electrical and electronic devices. And this is a very crucial problem in front of the scientific community, because this kind of waste is hazardous kind of waste which can have adverse effect, we can say that, on the human health as well as on the environment. So this is very important to pay attention on this kind of waste stream. And this is the electronic waste. So you can see these mobile PCB in the pictures, you can see computer motherboards, and you can see how the people are dealing with these waste. And this, if we will talk about the electronic waste, not only India, the overall world is facing this problem because of the continuous boom in the technology actually. Either it is the electronic technology, wireless technology, and whatever the technologies are there. So there is a continuous boom. You can see, you can take an example, means we usually like to change our mobile phone after every 1 year or 2 years. Specifically youngsters, they usually like to change the mobile after 1 year. And the same thing happens with the laptop also. After a few years, people like to change it. These are the two waste stream. Other than that, also there are various waste stream. So my means to say, what in this waste category, since we are the highly populated country, and within competition to the China, so India is the third most e-waste generated country. That is just for your information. And you will be surprised to know that only 10% of the waste is collected for the recycling purposes. So this is a challenge in front of the scientific community, specifically for the Indian government. And I will just talk it within frame to the Indian government. Otherwise, this is a problem which is just common for all the at the international level. And this is a document, the data which I'm presenting here. It is the policy paper of the MITI, Ministry of Electronics and Information Technology, Government of India. And 1 to 3% of the total solid waste in the developed country increases by 16 to 28% every 5 years. So you can see that this is something which is not going to stop in the coming years also. And this is the mapping of the e-waste. You can see at the world map also, you can see that yes, India is also there in the world map, you can see. But other than that, there are the different other countries, which clearly shows e-waste is a global problem. And on right hand side, you can see this plot where you can easily notice the growth of the e-waste in India. Starting from 2007, you can see 2025, and there is a continuous increase in the e-waste generation. And this trend, however, I have data up to 2025 only. We are currently in the 2025, but I can surely, I'm damn sure that this trend is going to continue actually, the way we are totally dependent on the electronic devices. So I'm sure that this trend will be continued, and we need to find out some alternatives. So we can't stop using the technologies actually, we should use. But at the same time, we should be aware that after the lifetime of this technology will be over, how to properly dispose it, how to properly manage it, so that it will not create any threat on the human health as well as on the environment. So that is the main goal. So this is the media spotlight you can see on the e-waste management in India. So these are the newspaper cuttings I have taken, and you can see that in the this newspaper on the this left hand side, you can see China is the number one in the e-waste producer in 2019, and after that is the USA, and India is also on the number third. And this is the annual e-waste output also, you can see, and which is continuously increasing day by day. And this is annual e-waste output at the world level also, you can see. So India sees the fastest growth in the electronic waste generation. So this is the Business Standard news in the 2024 term. More than 6,300 kg waste collected from the Noida only actually. So this is the newspaper cutting from the newspaper actually. So we are talking about 6,300 kg waste from the Noida. So you can see we have many metro cities in India. So you can easily assume the e-waste production in India. So these are the some other newspaper cuttings where you can see poses threat to the environment and health. This is the Times of India news, and e-waste, the growing threat we can't ignore. And India leads in the e-waste, how unused devices are impacting the future. So you can see that this problem is not just in the research paper. This is also covered by the many of the newspaper in the past. So which clearly shows the importance of this research area. Recycling has gone up in the last 5 years, but 60% of the e-waste remains unprocessed. Means this newspaper is showing that people are working on the recycling aspect, but only 67% of the e-waste still remains unprocessed actually, which is a problem. And it is an environmental pressing issue, and e-waste recycling comes at a heavy cost to workers health and environment. Why? Because the kind of recycling approaches currently used in India, they leads to various harmful gases. And because you need to burn the e-waste, or either you are processing it through some chemical route and all. So in both the cases you will see involvement of some harmful gases, which may be again threat to human health. So these are the few images I just want to show you, which is the current e-waste recycling scenario in India. You can see in these images how our people are manually segregating the e-waste, and which is not a good practice actually. Because and you can see in the image where the people are trying to burn it actually, and trying to process it through some chemicals actually, leaching route or something like that. So all these kind of approaches are not recommended, because having both can leads to threat to the human health as well as to the environment. You can see the people are currently using it. Why recycling it? Because e-waste having some useful elements which can be utilized for some other fruitful applications, specifically some metallic elements are present into it. So that's how the people are doing, but our way of doing is a bit different. So this is also one of the studies carried out by one of our colleagues in the metallurgical department of IIT where they are also trying to find out some kind of metallic element out of it, like gold, silver, copper, platinum, and palladium. So all these kind of elements are present into e-waste. Specifically, these are the different kind of e-waste stream, so which can be utilized for some other application. This is how our other research group in the at IIT BHU is working on. There is a one research group at IIT Delhi. So what they are doing, they are using this e-waste for the you know development of some filaments actually. So these days additive manufacturing or 3D printing is on the peak. Many of the people are using 3D printing technologies. RF and microwave people are also using these days 3D printing for the development of different kind of passive and active devices. Passive devices like meta surfaces, meta materials, and frequency selective surfaces, antennas, and all. So during the film 3D printing, you will see that the filament plays a very crucial role, and which is very expensive too. Actually, filament is a something wire kind of thing actually. So which through which we develop the different kind of patterns with the help of 3D printer. So IIT Delhi Research Group is using this e-waste for the generation of those filaments, which can reduce the cost of 3D printing. So that is the one application of the electronic waste. And there is another application of the e-waste. There is a one startup in the Mysore, and they are using e-waste for the development of some civil structures. Specifically, you can see some brick kind of thing. So you can see that there are two images of the bricks which are made up of the e-waste. This is how the different startup and different IITs in India are taking care of e-waste. And my research group is doing bit different actually, because we are trying to use this e-waste without any crucial processing or a typical process for the some applications, and that is the stealth application actually. That is today's theme. So stealth technology, that stealth technology, microwave stealth technology, infrared stealth technology, and optical stealth technology, we can see our research group is dealing with the microwave stealth technology. And this e-waste has the potential that it can be utilized for the stealth application, and this is first time reported by our research group. So the radar absorption or stealth technology, radar absorption, that radar is used for the radio detection and ranging. Radar is used to find out the location of any object which is far away from the radar, its location, its shape, its size, all those things. Through RCS we can find out, radar cross-section reduction. So complete information of any target can be find out. So what we are doing, you can coat your aircraft with the help of certain kind of radar absorbing materials or certain kind of structures like frequency selective surfaces or meta surfaces, so that instead of reflected back, all the signal will be completely absorbed by the this radar absorbing layer. So that is known as the stealth technology. Nothing will go back to the radar, enemy's radar. Everything will be absorbed by our coating. So this is known as radar absorber or microwave absorber. So the structure is something like this, that you have a perfect electric conductor, which I'm showing you here with the help of this brown color. PEC stands for perfect electric conductor. Over that you can see this green layer. So this green layer can be a layer of your radar absorbing material or radar absorbing structure. It can be a material or it can be any kind of structure, and it can be the combination of both also. The concept here is what that you need to deal with the impedance of this layer, which is dependent on the dielectric and magnetic properties. So we need to properly tune these dielectric and magnetic properties in order to provide the absorption, radar wave absorption at a certain frequency. And of course the thickness of the layer will also play a crucial role. And so incident signals are there, and we need to ensure that whatever the signals are incident on this layer from the enemy's radar, nothing should go back. Either it should be reflected into different direction, or it should be completely absorbed by the material layer. So that is what is known as a stealth technology or radar wave absorption. And so this is picture you can see. In this picture you can see this is the fighter aircraft, and how the radar is sending the signals to it and able to detect it. So if we can coat it with the help of certain kind of radar absorbing materials, nothing will be back to this radar, everything will be absorbed. And that is the goal of microwave stealth technology, or it is also known as low observable technologies, where we can use certain kind of nanomaterials, nanocomposites, and certain kind of periodic structures like frequency selective surfaces, metamaterials, meta surfaces, all those kind of thing to achieve this target. This is the other application of, these are some other applications of microwave absorber. It's not only stealth application, we can also use microwave absorber for your reduction of the RCS of an antenna side lobe reduction. To improve the performance of your antenna, we can use microwave absorbers. We can also use microwave absorbers for the development of certain kind of shielding structures, EMI shielding structures, which are very important for EMC, which stands for electromagnetic compatibility. And these are also useful for anechoic chamber, for clocking, for the development of radome. Radome is nothing, it is just the dome of the radar, cover of the radar, we can say that. So very good transmission is also required at the same time. RF energy harvesting is also one of the application is getting boom these days. So these are the different applications. As far as my research group is concerned, we are working on primarily on three different applications. One is the stealth technology, another one is the EMI EMC, third one is the anechoic chamber, and also on the low RCS antennas. So radar absorbing material, what are the radar absorbing material, how to develop them, what are the different types of these radar absorbing materials? So you can divide it into four categories. So the first category is the dielectric based radar absorbing material. So dielectric ram, in short form, radar absorbing material are known as ram. So dielectric rams, these are based on the concept of dielectric losses. Loss mechanism here is the dielectric loss, and these occurs in the mid to high frequency range. Their density is usually low, and their customizability is very high. You can easily customize them actually as per your requirement. Some examples are your carbon, ceramics, and polymers. These are some examples. If you come to the magnetic absorber, where we deal with the concept of magnetism, so these are the loss mechanism. Here is the magnetic loss, and frequency range is low mid frequencies. Density is high comparatively, which is a demerit, we can say that in some sense. And customizability, it is moderate, neither too good nor too bad. And if you talk about the what kind of material we should use, then microwave ferrites are the best actually. Ferrites, you can see in the RF and microwave books, there is a separate chapter on the ferrites, also microwave ferrites, which having various application actually used for the development of circulator, isolator, all those kind of thing. Yes, can also be utilized for the radar absorbing application. And magnetic metals also one such examples. So then we have the third category, where we have the conducting materials actually. So where the loss mechanism is based on the conduction losses. Frequency range is very wide, density is medium, either it is neither too good or not too bad, customizability is very high. And these examples of these are the conductive polymers actually, which is a very important class. Resistive sits can also be used. And now come to the combination of these three, means either you can mix dielectric or magnetic or conducting, any two out of three can be mixed together, then we call it composite. Composite means mixture of two or three elements, three different elements, that is the composite. And when the size is in the nano range, then we can call it as a nano composite, because these days you know there is a boom of the nanotechnology also. So when we reduce the size of this composite, that will become your nano composite. If you will talk about the loss mechanism, then it can be the combined loss mechanism. There may be the dielectric losses also. There may be magnetic losses also. There may be conduction losses also. In fact, this composite is the one of the very important class used for the RF and microwave engineering application actually, because here you can simultaneously achieve the two or different characteristic of the elements present. Because ultimately what we are doing, we are dealing with the electromagnetic wave having two important components, electric field and magnetic field, which both are perpendicular to each other, also perpendicular to the direction of wave propagation. So we need to clearly understand that synergy between those two field components. Based on that, we need to provide a synergy of the material also in the same way. Like you should have the combination of dielectric and magnetic material actually in order to achieve the important property. Neither a single element can't fulfill your all the requirements. We can go for the combinations, and that can lead to the composite actually. Composite means mixture of two or three elements, and if size is in the nano range, it is simply nano composite. So loss mechanism will be, of course, a combined loss mechanism. Frequency range is very wide. You can use them for a wide frequency range, which is the requirement for today's technologies. um, People are moving toward 5G technology, 6G technology, and when we will move toward the 5G and 6G. So one of the very crucial requirement is the what type of material I should use, what type of substrates are suitable out all those frequencies. Are these the normal substrates which are we are working at the lower frequency will be suitable for higher frequency also? No, we need to go for some other alternatives, and that time this concept of composite will be very fruitful. So density is the variable depending on your requirement. Either you can go for low density or you can go for a high density. And one of the very important thing is what their customizability is very high actually. And examples are the hybrids. Hybrids means is what combination of other three, about aforementioned three. So the concept of this radar absorbing material or microwave absorbing material is not new. The concept was, there in the 1936 Netherlands. So they developed the first uh, microwave absorbing material, which was made up of the carbon black and TiO2. But the frequency range was only 2 gigahertz for their material. It was utilized for the shielding application. Then after that, inspiring from them in 1945, Germany was very active and they developed two absorbers, Wesch and German. And the name of these two is dependent name on the based on the name of their scientist. They first time used it during the World War II actually. So for specifically for submarine application, and it was made up of some rubber sheet actually at 3 gigahertz, and there was a wideband absorber also, which was based on a multi-layering approach actually. German, it is based on the not a single layer, there are the multi-layer of the absorbing layer. And so it was a wideband absorber which was in the frequency range of 2 to 15 gigahertz, which was also utilized for the submarine application. USA was very active in that direction later 1948, and they developed one absorber for the ship application actually, and it was made up of some iron particles which were mixed in the neoprene actually. It was operating at the X band, which is also known as the defense band, having frequency range from 8.2 to 12.4 gigahertz. Then USA was very active during the 1950, and where they have used the animal hair actually. Surprisingly, they have used in the animal hair. Animal hair were dipped and coated with the help of carbon onto it, and they utilized it for the anechoic chamber application for outdoor antenna measurement range, also all those kind of things. Then USA was very active actually. And 1952, 1956, 1960, 1970, and up to 1989, they developed a series of technologies actually based on absorber. And Salisbury screen was the first, which was used for the quick chamber design. Circuit analog absorber, where you can use some circuit elements, where you can use some chip registers, you can use some registers also for the development of the absorber. And you can use some magnetic absorber, as I have already told you, which are made up of the microfarad. So these two technologies you can see in the 1960 and 70, where one is the microfarad, another one is the high lossy layer in front of the ground plane. These two concept, magnetic absorber and Dalbach layer, they were utilized by them for the stealth technology actually, stealth application. So as I told you, absorber having many application like EMI shielding, like stealth technology, like RCS reduction. So these were the two important development by the US, where ferrites were first time utilized for the radar wave absorption. And then they have developed one paint also, which is known as Halpern anti-radar paint, for the airborne applications, for the aircraft application, actually stealthy aircraft application, where high The artificial dielectric material of very high dielectric constant actually can be utilized for the development of radar absorbing paint. And chiral absorber, where which is based on the concept of optical activity and circular diachromism, can also be utilized for the RCS reduction, is invented by the US. And as far as concerned with the India, so our technology is also, we are also doing great in this field of stealth technology, radar wave absorption. We have our own HAL Tejas, which is developed by the HAL Tejas, and Ajit are our two stealthy fighter aircraft available in India. So Tejas is the first indigenous fighter aircraft jointly developed by AD and HAL, and we have Ajit also. And I'm also happy to share with you that this development of this Tejas, our honorable chairman of our board of governor BOG of IIT BHU, Professor Kota Harinarayana, was in the lead role of this development of this Tejas at that time when it was developed. And we have Ghatak also, which is a stealthy unmanned compact air vehicle. We have Vajra stealth drone. We have Swift UAV and Vindhyagiri and its launch you can see here. So we have a number of stealth fighter aircraft. A few of them are developed by us based on our own indigenous technologies, and a few of them are developed under the joint venture of India and Russia. And so this is the Indian stealth warship. Also we have like Shivalik, Satpura, and we have some Talwar class of series like Talwar, Trishul, Tabar, Teik, Tarkash, Trikand. These are our different stealthy ships also. So this is I mean to say what we are also not behind as far as this technology is developed in this continuous technological growth era of this particular important area of the research. Now, what are the ideal requirements of an radar absorber or microwave absorber? So it is not only that you need to absorb. It is not only the one requirement. Yes, absorption is the important requirement. Means you should have the minimum reflectivity and minimum transmittivity. Means we want to get the maximum absorption, but that maximum absorption is nothing if you are not getting that maximum absorption at a wide range of frequency. So that is another important requirement, that my absorption should be in a wide range of frequency. Means there should be a wideband absorption. Other than that, there should be polarization insensitivity, there should be angular stability. It doesn't matter from what angle the wave is falling on my object, it should be able to absorb all the radiation. Other than that, these are the few important parameters which are important as far as RF and microwave engineering is concerned. But other than that, also many other important factors are there, like agility and speed. And speed of any fighter aircraft, it will depend on the weight also. And this radar absorbing layer is also going to contribute some weight to aircraft, which can affect the speed and all. So, my means to say what we need to pay attention on the density and we can say the thickness of the absorbing layer. That is also very important. But that is the challenge actually. To achieve all these important RF and microwave properties like minimum reflectivity, wideband RCS reduction, polarization sensitivity, angular stability, at the same time, when the thickness should be down and weight should be less. So that is a very important thing for a radar absorber. And not only that, you need to take care some environmental point of view also, like whatever the layer you are using on the aircraft, that should be chemical stable, should not be affected by any kind of chemical, it should not be affected by any kind of rain and moisture. Okay, and it should not be affected by electrical hazards, specifically lightning problem, which is the one of the very crucial problem in this sector of aerospace engineering. And of course the layers should not be affected by any kind of corrosion, etc. So it's not only that just to develop an absorber which is providing good absorption in our lab, but is it going to pay the same thing, provide the same kind of capability when it is in the field? That is also very important. And aerospace engineering point of view, your structural robustness, also your mechanical strength actually, which is very important. Either your absorbing layer is able to withstand different kind of stresses or other kind of condition, because the time when the your aircraft which will take an actual fly into the sky, that time different kind of forces may also be acting on your aircraft, and you need to be handle those things. Means it should not be like my absorber is absorbing at the ground, but when it is taking the actual fly, that time its mechanical strength is not that good, it is not able to withstand on the aircraft body. So all those points are critically important to be put with the consideration when we are dealing for the actual product development. And these are the major challenges in the development of a microwave absorber or radar absorber. It is not that easy to develop this kind of absorbing material, specifically if you are interested in the product development, because there is a trade-off among certain factors. And what are those factors? Like I already told you that these are the different factors like maximum absorption, wide absorption bandwidth, lightweight structure, angular stability, polarization sensitivity, tunability, and specifically cost effectiveness for a developing country like India. So, how to achieve all these factors together? Is it possible to achieve all these factors together? No, it is very difficult actually, and there is a challenge. There is a trade-off. When you will try to achieve one or two factors, that will be at the expense of other two, the other factors actually. That was a challenge few years back. Many of the peoples are still working on this technology. That is still a challenge actually, and that is a very open problem for the research, that how to achieve all these factors together at the same time to achieve good mechanical properties, to good chemical properties, all those things. So that is a challenge. So what is the solution? So solution is we need to adopt a multidisciplinary approach, certain kind of holistic approach where we are not dependent on a single branch of the engineering. We should try to provide an interface between different branches of the engineering, and then only we will be able to develop a product. And this is true for any kind of product development, but specifically as far as today's topic is concerned, you should have the knowledge of these different areas, or we can say that branch of the engineering. Yeah, so first of all, field and wave theory. We also called it EMFT, electromagnetic field and wave theory. So yes, the knowledge of field and wave and how it is interacting with the media, that is very important. Materials engineering and nanotechnology, so that is also very important to understand, because everything, whatever the RF and microwave devices we are simulating in the HFSS CST. And also, first of all, the very important thing is the what kind of materials are suitable actually, specifically for the 5G and 6G technologies. So that material selection, you should have some knowledge of the materials engineering. And since I already told you that these days there's a boom of the nanotechnology. People are talking about nanomaterials, nanostructures. So the knowledge of nanotechnology is equally important. The knowledge of electrical electronics engineering is also important, because in the development of radar absorbing materials or radar absorbing structures, it is not only the materials. Sometimes you need to use something kind of electrical electronic the devices too. Like for example, you need to use a diode if you want to achieve the tunability. You can use a pin diode, you can use varactor diode, or you can use some certain kind of chip registers to provide the external losses to the system. We can use some registers also, actually normal registers also you can use. And if you want to control these arrays of pin diodes and your this varactor, then you need to use some FPGA board also, some art kind of Arduino board also actually. So that is where the electrical electronics engineering will be there into the picture. Communication engineering. So first of all, you should be aware about the transmitter, receiver, how they work, how the this thing free space losses and all those kind of thing. So the generalized understanding of the communication engineering, antenna and wave propagation is very important. Mechanical engineering, specifically aerospace engineering, which I have already told you, because we need to also consider the mechanical strength of these structures, specifically when we want to employ them on the aircraft body. And in general also, even if you want to use them on the ground, then also it is very important to understand the knowledge of this mechanical engineering. Computer science and engineering, that is also equally important, because these days the kind of structures we are using are sometimes are multi-layered structures. Sometimes it is a combination of nanomaterials and meta surfaces or meta materials. That time there will be the huge design variables actually, and when you will do these optimization of these structures with the help of your optimization tools like CST and HFSS, it may take more time. So in order to save the time, you can go for certain kind of algorithms, you can go for certain kind of artificial intelligence approaches, machine learning approaches, in order to save your time actually, and which can very fast way can optimize your design. And design itself, yeah, so overall design is also very important aspect. Many of the IITs are running this design as a separate branch and running the courses like BDes or MDes in India these days. So the knowledge of design is also very important. The overall structure design, of aircraft also, and structural design of your radar absorber layer also. So that is also very important to achieve the property. So the fusion of all these approaches can lead to some kind of result which can give you the which can be helpful for the product development. So this is what I want to show you, the kind of experimental work carried out by our research group on the electronic waste. So I will start with the very simple waste stream we have used. So first one is the PCB. Actually, these are the PCB you can see, which is extracted from the used mobile phone. And that year I still remember I have taken it from one vendor, the Nokia, this thing, because Nokia mobile phone were of no use that time. So we got a lot of PCBs from the vendor, local vendor, and these are the some batteries actually you can see, which is the zinc carbon battery. I'm sure you all have noticed these in your different electronic gadgets. This is the third kind of e-waste you can see here in this image, third image, which is the lithium ion battery actually, which is in our laptop and all those kind of stuff. So we have initially tried these three kind of waste stream, where PCB boards are there and these battery cells are there, lithium ion battery, and this is my zinc carbon battery. These are the different kind of images, SAM images at the micro scale we have captured using the scanning electron microscope, and which clearly shows, you can see the particles, because the naked eyes, when you will see the powder form, these kind of thing, you will see that these will look like like black color of powder. But in actual, when you will go to the microscopic level, you will see that they have different kind of morphologies, means they have different kind of shape, different kind of size, and that shape and size directly contribute to their dielectric and magnetic properties, means frequency dependent dielectric properties, frequency dependent magnetic properties. And when you will change the size, their dielectric and magnetic property will also change. So you have a flexibility, first of all, that you can play with the dielectric and magnetic properties depending on your requirement. And we have taken converted it into the powder form, and then coated it on different sheets, and we tested it with the help of waveguide setup and free space setup. And before I'm going to directly come to the result of those properties of the waste, I just want to discuss with you this very important slide. So you can see that this is the sample under test SUT, where we have storage and losses. The sample under test is nothing. This is my electronic waste in this case, which is made up of PCBs, discarded PCBs, and zinc carbon battery cells. So this is the electromagnetic wave having two components. I've already told you, electric field and magnetic field. So we have permittivity, very important characteristic of a media, where we talk in within reference to the electric field. Permeability, another very important characteristic of the material, where we talk with reference to the magnetic field. And you can see permittivity is nothing, permission given by the material to enter the electric field inside it. So permittivity word is coming from there. Permeability, it is coming from the word ability to magnetize the material. So both these two parameters are complex quantities having both real and imaginary parts, where you can see real parts represent the energy storage and lossy parts represent the energy losses. If you want to develop a good radar wave absorber, you need to properly choose a certain kind of media where you can properly tune these properties, real and imaginary part, because both are equally important. Specifically imaginary parts, its value should be high, because we are interested in the more losses when we are interested to achieve the absorption. So these are the goals actually. So if we are working on the dielectric medias, then permittivity will be come into the picture. If we will dealing with the magnetic medias like ferrites, then permeability will be there in coming into the picture. But ferrites is a very important class, where you will also have some dielectric properties also. So ferrites is important in the sense because it will provide both the dielectric and magnetic properties. And tan delta, which is known as loss tangent, which is nothing, just the ratio of these two, imaginary and real part, is again very important. So a synergy between these permittivity, permeability, and conductivity also, you can say conductivity is also, which can come from the imaginary part of permittivity actually. So these three property, permittivity, permeability, conductivity, and loss tangent, all these factors will decide either your media is going to absorb or not. So, and specifically, if I just want to tell you that these properties are frequency dependent. So, and that is why it is important. I was discussing with you that for 5G and 6G technologies, we need to search what kind of medias are suitable. Specifically, when we will go to the terahertz and all, what kind of medias are suitable to act as a good absorber, good antenna material, or whatever the other kind of RF and microwave devices we are interested in. So that's very important, and that time frequency dependency will be there in the picture. So you can see this slide where I am just showing you a plot where we have real and imaginary part of dielectric this thing permittivity, and we on the x-axis I have frequency range, and frequency range is also stays radio, microwave, and you have infrared and UV. So you can see the pattern. The first of all, you can notice this figure that my properties are frequency dependent actually. So, and that the way frequency dependency is there is also different from different part of electromagnetic spectrum which is on the x-axis. So when we'll talk about the RF and microwave frequency, because our today's topic of discussion is the RF and microwave based radar absorber only microwave style technology. So that time you will see the kind of polarization which is very important, the dipole formation and the polarization. So this is a very important concept. So orientation polarization or the dipole polarization, that will be there in the picture. Microwave oven is the best example to understand this. So when you put your food item inside the microwave oven, so the microwave which interact with the food item, there is a dipole formation, and one side you have the positive, on another side you have a negative. Dipole start to rotate at a very high frequency, which is the operating frequency of your microwave oven, 2.45 gigahertz. And it there will the friction, there will be the different kind of losses, and that's why your food get heat treated in a fraction of the second. In the same way, that is the dipole orientation polarization actually, which take place at the microwave frequency. In the same way, when you will talk about the infrared frequencies, that time ionic polarization will take place. When you will talk about the ultraviolet, then electronic polarization will take place. If you will go down to the RF and microwave frequency, you will go to the megahertz range, then you will see the interfacial polarization or space charge polarization will take place. So my means to say, what polarization is the main cause of this frequency dependence in the property, and this polarization depends on the what kind of media we are using. And another important thing, the kind of polarization mechanisms are different when we talk about the different frequency range of the electromagnetic spectrum. For microwave range, it is orientation or dipolar polarization, but if you go to the higher frequencies, then it will be the ionic and electronic polarization. If you will go to the lower frequency, then it can be the interfacial or space charge polarizations. So these are the frequency dependent property of our e-waste. So you can see these are the two different e-waste samples. So dielectric constant you can see is in the range of something like 9.5, something like that. We have this imaginary part also, it is going up to 6, 5.8 or 5.9, approaching up towards 6 in certain frequency range. And magnetic properties are not that appreciable, because yes, e-waste is a pure dielectric media. And you can see the second sample also, where dielectric constant is going beyond 10. It is around 11, and there is a reasonable imaginary part of our dielectric properties, our permittivity. So these kind of properties, why these kind of properties are coming into there? Because of the kind of elements are present into e-waste, like e-waste having some dielectric component. It's also having certain kind of magnetic element like zinc. It's having some carbon. So all these kind of elements can provide you good dielectric properties at the same time. So these are the certain plot you can see where this is tested in the X-band frequency range, 8.2 to 12.4 gigahertz, and reflection coefficient is there on the y-axis. And you can see the minus 10 dB bandwidth. You can notice for these different type of samples. The T stands here for the thickness of the absorbing layer, which is utilized for these results. So you can see the sample having the code BL. So that is at the 1.9 thickness, is providing very good bandwidth actually. Minus 10 dB bandwidth is around 3 gigahertz, and it is providing the minus 27.86 dB um, um, reflection coefficient at the 1.9 thickness. So this is a one important result. And then frequency selective surfaces, which is a kind of electromagnetic filter. Many of the people are working on this topic, and it's a kind of electromagnetic filter which can provide the special filtering, electromagnetic filtering capability depending on your application, depending on your requirement. Starting from your microwave frequency range, you can go to the terahertz and infrared regions, and their properties are dependent on their shape, their polarization incident angle. And you can see this is the high pass filter, the just the Babinet principle. If you will apply the Babinet principle, just reverse of that, you can have the low pass filter, you can have band stop filter, you can have band pass filter. Depending on your requirement, you can have either the band stop or band pass response. These are the different kind of geometries which are available. We published our first article on the we published many article actually before 2017 also. But this was the one review article we published in the year 2017 in very prestigious journal of LC, or Aerospace Science and Technology. And it is the most cited and most downloaded article of the journal I have published so far, where different type of FSS structures you can study, starting from your traditional FSS, fractal, your active, layered structure, cascaded, your 3D FSS, also textile FSS, dielectric or graphene based FSS. And so now, what my means to say, what e-waste can provide the absorption, but it is possible to convert the e-waste is also into certain kind of uh, FSS kind of thing. Yes, so this is what you can see in this research. You can see that this is the e-waste layer, and inside the e-waste layer, what we are doing, we are creating certain kind of perforations. Actually, you can see perforations, and these perforations are created at a regular interval. And this is a periodic kind of perforation, square perforation, and which are created into the e-waste layer. Why? It will help in a two ways. Number one is what, that by creating this perforation, my weight can go down, weight of the absorbing layer. And number two, now since the structural effect is also coming into the picture, earlier it was only the material effect. Now structure effect will also be there into the picture. So due to this structure effect, what we can do now, we can have some certain kind of uh, we can play with the angular stability, we can also play with the polarization insensitivity also. All this kind of thing also we can do. So that's a very important thing to see here. And but the again important point is what, can we do random perforations, or can we do any kind of perforation into it? No. Again, it will depend on the what kind of media you are choosing. Actually, depending on the dielectric constant, this perforation will be chosen. Actually, its shape, its size, everything will be chosen depending on that. And another important thing, what should be the size of these perforations, because you can see there are the squares. Of course, square having certain length and width, the gap is also there. All the concepts which are applicable on the FSS will be applicable here also. And instead of conducting FSS geometry, we should call it like a dielectric FSS, because it is made up of the dielectric material now. And at that time, these two equations you can see, which are based on the electromagnetic mixing models, will come into the picture, which will provide you certain kind of understanding. Because this gap we are saying, but in generally this gap is the air. Actually, here in between, air is also one kind of media, and this e-waste is another kind of media. So how this electronic waste is hosting this air gap in between, that can be understand with the help of electromagnetic mixing model. So in the modeling itself, we need to introduce those electromagnetic mixing model equations here, then only we will be able to create these perforations. So that is the part of we have used certain kind of optimization algorithms to do that. And we validated those algorithms with the help of full wave simulation tools also, where we can choose the what kind of perforation I should use and what should be their dimension. And you can see after doing creating these perforations, absorption response is significantly improved. Actually, so very good absorption response is achieved. So at the same time, the structure weight of the structure is also reduced. So this is a important concept. And now I'm just want to show you some work relevant to the radome technology. So certain kind of materials, e-waste materials, can also be utilized for the antenna substrate application and for the radome development actually. So it is a, you can say this is an antenna, so you need to use certain dielectric substrate here. So a certain kind of materials we can e-waste based material which can be utilized for the development of this dielectric substrate, and also the cover of the antenna, which we call as a radome. So that is very important thing. So this is the work which is I just want to show you. This is the work carried out by my two amtech students, and both of the amtech students are mechanical engineer actually. So we utilize their skills, mechanical engineering skills. I utilize my electronic skills, they utilize their mechanical skills, and we develop something here, which just I will show you. Just a minute. So what we did in this study, you can see that we have chosen an HP laser printer, and it's a cartridge we have used actually. You can see in these images. So this is the discarded cartridge when it was of no use, and we dismantled it. So student was the mechanical engineer, so he was well able to do this exercise, and then we converted it into the powder. Powder was extracted out of it actually, and we nothing to convert it actually, it was already there. And then we developed a palette, and this palette was we did this testing for our C band, and these are the different kind of studies just to find out, because when we are saying waste we need to understand what kind of elements present into it. So we performed certain studies to find out what kind of elements are present into it. So we find out that you can see carbon is present, iron is present, oxygen is there, silicon is there. So just pay attention on the top four, top three I would like to say. So carbon and Fe, and and percentage also you can see carbon is present in the abundant 54.52 percentage. These are the morphologies, images captured at the at your uh, microscopic level actually, scanning electron microscopy images. And Fe3O4, which is a magnetite, which is a kind of ferrite also actually, that is present into these, and which makes their properties very interesting to us. You can see here dielectric constant is 3.8. The important thing which you can notice is the lossy part, it is very low actually, and low stringent applications can make them suitable for for these applications, for antenna substrate applications and for radome applications. But we can't use powder directly actually, we need to convert it into some form. And for that particular purpose, my students, they have developed one setup in our lab itself. It is a very low cost setup they developed themselves. They utilize their full mechanical engineering skills, and they developed one mold. They developed this setup in the lab, and this is, you can see, sealed and vacuum. This is setup is based on the vacuum pump actually. And this is the final product actually. You can see in the last image in this figure below, this is the final ready composite sample actually, this black color composite sample. So this is the final composite sample, and we use certain kinds of fibers into it, because when we talk about the FR4, you can see FR4 is what, it is the glass epoxy fiber glass epoxy actually. So we have also used some fibers here, and I'm very happy to share with you that the kind of fiber we have used here is also only available in India actually. It is directly coming from the nature. So that makes this topic very interesting. And so this is the final image you can see of this panel, which is very flat actually. This is a very flat panel. It is made up of those your cartage ink and epoxy, and your those fibers. And we develop different type of these panels. And we just first check their morphologies, and also you can see these images how well my this these are the images at the micro scale level. So you can see how well my battery, this cartridge particles are impinged into those fibers. Can you see these fibrous kind of structures? These fibrous kind of structures are nothing, these are the those fibers which are embedded in between in the development of composite panel. Why we are using these fibers? These fibers have nothing to take with the RF and microwave performance. RF and microwave performance is contributed by only cartridging. Okay, this panels are these fibrous kind of structures are helpful to achieve the mechanical strength. So because our goal is not only to get the good electromagnetic performance, if simultaneously we need to achieve good mechanical performance also. That was the goal actually. And in this sense, so this research is too interdisciplinary, you can see. So these are the some certain kind of dog shape kind of sample we have cut down as per the ASTM standard to check the mechanical strength. You need to check up to what level these sample will withstand its property and it will not break. So this is the stress or strain characteristics, and you can see this is the my original sample. Right hand side is the fracture sample, which is clearly showing its capability that it can withstand this much of the stress. Actually, this much of the stress or this much of the strain it can achieve. It clearly indicates this mechanical strength actually. And then these are the properties of the panel actually. So you can see the dielectric constant of the panel is varying in different range. It is 2.8, it is 3, 3.3, and the lowest tangent is also it is 0.05. Okay, so different samples we tested with the help of our setup in the real time, and S21 value is also, you can see for the red color, you can see it is minus 1.5. So we are still trying to powder, prepared a palette initially to check the media properties, and then you can see that this is the final structure. You can see composite panel structure is there, another in the same way as we shown you for the previous structure. And again you can see these are the some microscopic images of the panel, because when you will see this panel through the naked eyes, it will look like just a black color sheet, but we need to understand the inner, what is inside it actually, and how the things look like, which we can't see with the help of naked eyes. We need to use certain kind of microscope, and electron microscope is the one very effective tool to see this. Scanning electron microscope, where beam scans the surface of sample and you can see
Excuse
these
me, sir.
images. Yeah, hello.
Sorry to interrupt you, sir.
Yeah.
Your screen is not visible right now.
Oh, screen is not visible.
Yes, sir.
Okay, let me again show you. Yeah, so I'm again sharing. So I hope now it is visible.
Yes, sir. Yes, sir.
Yeah, it is
Now it
visible.
is visible.
So yeah, so should I start from here? Have you seen the solar cell based slide?
Yes, sir. From here you can start.
Okay.
Huh.
So this is the solar cell waste which I was discussing with you, that this is the second waste stream. So I have shown you three different kind of waste stream till now, four different kind of waste stream. The first one was what, PCB board, which were coming from the mobile phones. The second one was the zinc carbon battery cell. The third one was our lithium ion battery cell. All those three streams were useful for what? A stealth application, radar wave absorption. Now two waste stream I am showing you, which can be suitable for your antenna substrate application and radome application. The first one was my cartridge ink, and the second one is the solar cell waste. So this is the solar cell waste. You can see that how the solar panel was taken and it was converted into the powder through some mechanical processing, finally into in the form of a pellet, and this is the final sample which is fabricated by our students. So this is the made up of solar cell panel only with some fiber into it. And so this is the morphological and elemental analysis of this. So what you can see here, that how well my solar cell particle are impinged into the this fiber structures. So when you will see this same sample through the naked eyes, that's what I want to show you. it will look like a plain black sheet. Can you see here that this sample, fabricated sample, this is looking like a plain panel actually on the top. But if you will go to the microscopic level with the help of electron microscope, where electron beam scans the surface of sample, you can go into the deeper actually, and you can see and the kind of structure. So this kind of thing clearly shows you the reason behind the your mechanical strength actually, because of the bonding between epoxy and these fibrous layers. And of course it is also going to contribute the electromagnetic performance also, because what we have observed in the past, that the morphologies, shape and size, as you can see, metamaterial meta surfaces we call one unit cell. So in the same way here also, when we'll talk about the atoms, when we'll talk about the particle shape, particle size, that also going to contribute to my dielectric and magnetic property. If you can find out certain ways to change it, you can change your properties also actually. So elements present into it, again there is a carbon, oxygen, silicon. So silicon is present here into it, of course, because it is a solar cell. So these are the again dielectric properties you can see, and low stringent properties, and S21 characteristics. So dielectric constant is again, it is around 3.6, and low stringent is again it is low value compared to the absorber. Specifically the low C part is very low, and S21 is also around 1.8. So this is the thing. So this is what I want to show you, that e-waste can be effectively utilized for different kind of RF and microwave engineering application. But there is another thing also. Why to generate e-waste? I now just I want to present you the another story. Why to produce the e-waste? Why not to develop certain kind of gadgets where there will be the no e-waste production, or if e-waste is produced, that amount can be reduced actually slightly. So this is known as circular economy actually, a way forward to management the e-waste. So it means what we are doing up to now, that we are generating e-waste, and then we are trying to find out the ways to how to reuse it actually for certain application. But isn't it a good way that there is no need to generate the e-waste? You develop certain kind of electronic devices where we are using some natural products for the development of our these electronic gadgets. So after, once the lifetime will be over, so it will be completely we can say that completely discarded actually, and it will be environmental friendly also at the same time. So this is what the concept is. So biodegradable electronics, we can say that, which is the future of sustainable technology, where idea is what, that electronic component can't be reused or recycled, it should be biodegradable in the nature. So that can be the one innovative technique where you can where you can interface the electronics with the environmental consciousness. And this is the WE statistics and highlight. So I just again want to show you, this is a dimensional map where you can see the electronic waste number of publication on this e-waste problem actually. So you can see how many papers are published actually. People are, many of the paper are on the recycling e-waste, are on the repair or reuse of the electronics. But you can see there are some paper people are coming with where there are some biodegradable electronics they are talking about in this e-waste paper only. Amount is less, you can see in this curve, but yes, there are some research work is currently going on. So this is what I want to show you. Like you can see there is, this is simple, your I see where you can see you have the different parts of the circuit elements are there, transistors are there, antenna are there, capacitor, interconnect, memory, register, battery, all those things are there. So is it possible if you can make these components of certain kind of biodegradable material? So then you will have the two type of PCB waste. One will be my PCB waste, which is a problem in front of me, but if I can convert it into the degradable PCB, then e-waste will not be a problem. Yeah, task may be challenging again, no doubt, but we can think in this direction. This is just a point to think of actually. So this is what I was talking about. So you can talk about the device level sustainability also, and you can talk about the part level sustainability also. Means you can make the whole device which is made up of the biodegradable material, and you can talk about certain part at least made up of the biodegradable material. So this is what we can do, and certain research group are also working on this technology. Like I want to show you one biodegradable electronic display on by the Printed Electronic Research Group, Karlsruhe Institute of Technology, KIT, Germany, one of the very prestigious university in the Germany, and they developed one, this kind of biodegradable electronic display. You can see images also there, and it is made up of the P.PSS actually. and the cellulose diestate was used as a substrate, and then organic polymer p dot pieces was printed over that, and it is a very useful thing which can help us to develop something like biodegradable electronics. There is some other things are also there, like environmentally safe electronics that also vanish in the body actually. So some kind of electronics which you will put it into the body, it will work well during its lifetime, and after that it will vanish in the body itself actually. So this is the biodegradable integrated circuit which is implanted under the skin of a lab rat. You can see here it is the image, and this is the another study, biodegradable integrated circuit which is during dissolution in the water. So these are the two technologies which are based on environmental friendly technologies actually, and this is developed by some Bachman Institute, University of Illinois, Tufts University. So these are developed by different foreign universities actually, and this is now come to the antenna. So this is the printed microwave metamaterial antenna circuitry is on, and it is made up of what? It is made up of palm tree. So palm tree extracts, and it is mixed with the nickel oxide nanoparticles, and it is hosted into the polyethylene, and then it is utilized as a high gain microwave antenna actually. So this is the another application. It is published with the Nature Scientific Reports actually. So these are the different kind of ideas where people can go with, and these are the few textbooks which, if you want to go more insight into the e-waste, different kind of the e-waste streams, then these are the few books published by reputed publisher like Springer, Will, and all. And concluding remarks. So yes, it is very important to find out the different ways to effectively utilize the e-waste, and to develop the more innovative methods where we can utilize the e-waste specifically for the a certain kind of applications where we no need to dependent on chemical route or certain kind of um, uh, routes where harmful gases are evolving out of it and all. And most importantly, we should also try to develop something biodegradable type of devices, so that this e-waste problem can be reduced to the great extent. These are the research work which is carried out by my different PhD student, my master students, and we are only guiding them actually. Otherwise, this is the whatever I have shown you is the really the hard work of my dedicated research team at ITBHU RNC, and my old institution also, Triple IT Jabalpur. And this is the international research collaborations we have in different institutions which helped us to time, and these are the different funding agencies which supported us to carry out the different kind of research activity in our lab. And thank you very much for your time and attentions. Yeah, I'm open for the discussions now.
Yes, sir. Thank you very much, sir. Participants can ask the question, and if you want to ask directly, you can just raise your hand. We will open the mic for you, sir. Sir, the first question is, in case of absorber, what
Yeah.
parameters we have to take care for choosing the better substrate material? Is it permittivity or loss tangent or both the things?
Yeah, so it's a good question. So in general, low tangent basically, because we are interested in the, to absorb the radiation, so there should be the good losses. But yeah, permittivity is also very important, because I was talking about the miniaturization. I was talking about some, I was talking about certain kind of things where lightweight structures are desirable, and if you are to go for the lightweight structure, that time thickness should be less, so permittivity should be high. So you should pay attention on both the part. Permittivity also means complex permittivity, you should pay attention, better to say complex permittivity, having both the real and imaginary part, as I have shown in the slide. Permittivity is a complex quantity having real and imaginary parts, so we should pay attention on both the parts actually.
Thank you, sir. Any more queries, participants? You can please ask.
Hello,
Hello.
sir.
Hello.
In case, hello, sir.
Yes, I can hear you. Yeah, please.
Sir, in case of absorber, when we
Hmm.
are using absorber as an stealth technology,
Hmm.
then we have to calculate uh, SE, shielding effectiveness value.
Okay.
So in the formula of shielding effectiveness, there is a term S21,
Yeah,
and only that term is remaining. Rest S11 will cancel out.
yeah.
And we already know in absorber when we are placing ground plate so that no transmission will take place. So how can we put these S2 value for the calculation of shielding effectiveness?
Hello.
Hello.
Yes, sir. You are audible now, sir.
Yes, yes, but Vikram was not audible to me, so I was only able to just he was talking about some shielding effectiveness, SE. Yeah. So Vikram, yes, you could you please repeat your question? So yes, you were talking about SE. Yes, yes, shielding
Yes, sir.
effectiveness.
My
Yeah,
question is, sir, in case of absorber, when we are placing ground plate completely metallic plate, so
yeah.
no transmission will take place. That means our
Okay.
S21 will nearly equal to zero.
Yeah, true.
And
Yes.
when we are placing that value in SC formula, then we
Yeah.
will not directly observe the perfect SC value. So how
So
can we
Vikram,
find out this S21 value?
yes, so it is true, Vikram. You are absolutely right. But here you are merging two concepts together, which are different. If you have noticed my slide, I have shown you today the applications of microwave absorber, where stealth technology was the one and EMI shielding was the another. Okay, so these are two
Yes.
different concepts actually. You can't merge them together, and structure-wise also these are two different concepts, right? So when I'm
Okay.
talking about the stealth technology, only that time I will use the pack. When I'm going to talk about the EMI shielding, there is no pack, so we can't
Okay.
make these two concepts together actually. In the case of pack, you don't have any kind of those
Ground
you
plane.
don't have any pack here, ground plane. So, and
Okay.
second thing, SC is a more complex phenomenon actually. Now, yeah, both concepts can be interrelated with each other, can be interconnected with each other, but are not same actually. So SC is how SC is interconnected with the this thing absorption. I can say that absorption is the one contributor to the SC, but reverse is not true. Getting my point?
Oh,
Mine, when I'm
oh,
calculating the SC, absorption will
oh.
also be the one of the major contributor that time. Okay.
Yes, sir.
Yeah. So that is the thing. But that is not the width path. That there I'm talking about the media property only. And okay, so I'm talking about only the medium property, the material layer only, nothing else.
Okay, sir.
And when I have material layer, and depending on the material properties, anything absorb, or it can pass, or it can transmit, or it can reflect, depending on its properties actually.
Property. Yes, sir.
Yeah, so SC is an entirely different concept actually, that has nothing to take with the stealth technology.
Okay, sir. Okay, okay, okay. Thank you, sir.
So next question is, can you please tell the procedure of
So,
finding the
so
permittivity?
yes, yes. So Swati, so I can read the questions now here. So
Yes,
let
sir.
me read the question and then I can take it one by one. So I think Vikram question is already taken. So then Dr. Anandi is asking, kindly tell me the procedure of finding permittivity of such biodegradable materials. So Dr. Anandi, so thank you for asking the question. So you can find out the permittivity of these biodegradable material. You need to go for either, there are various methods actually to find out. So there are the transmission line methods. So transmission line methods can be divided into two types. There is the waveguide method, is the one method through which you can find out. There is another method, it is known as coaxial airline method. You can find out permittivity using that also. There is a resonator cavity method is also there, where we use the cavity. You can use a free space method also, free space method, which in the quick chamber also, where two antennas are there. One antenna is going to incident, another antenna is going to transmit the signal. You can find out the scattering parameters, and then all four scattering parameter, S11, S21, all those four kind of scattering parameter, and you can use the NRW algorithm actually, which is a well known method to convert scattering parameter into permittivity values, permittivity and permittivity values. So these are the well known technologies are available. So means there is no specific method is required for the biodegradable material. All the existing methodologies which are there to find out the dielectric constant will be applicable on the biodegradable material. I will recommend to go for transmission line methods to do that. So after that, the next question, suggest specific journal or journal which has scope on this biodegradable material antenna. So Dr. Anandi, I think there is no separate journal. All the journals which publishes the paper on, your normal antennas article will be suitable for biodegradable antenna also. Like if I talk about the IEEE transactions on antenna wave propagation, IEEE AWPL, IEEE MTTT will give a very good scope to this, and IEEE transactional microtheory and techniques. And you can go for the IEEE transactional dielectric and electrical insulations. And if your material is the magnetic in the nature, then you can also go for IEEE transactions on magnetics. And rest of the journals, I think each and every journal will provide the space to this topic. Reverse engineering using VNA is acceptable, sir. Reverse engineering using VNA. Reverse engineering means you are talking about that you take all the scattering parameters and then convert it into epsilon mu. That is the meaning of reverse engineering, or something else you please mention here. And if possible, you can also make yourself unmute and can discuss with me one to one.
Dr. Anandi ma'am, you can unmute yourself. We have given you the access. If you want, you can unmute.
Hello. So, Dr. Anandi, if you are unable to unmute, you can write here. Means, what is the meaning of reverse engineering? So, I think there is some problem, Swati. So, you can give my contact number also. It is already there in the slide, and anybody can call me this thing and can discuss via email, or they can directly contact me via mobile phone. Also, no issue for more
Okay.
discussions.
Yes, sir, I will do
Because
that.
I'm not getting any message further here. And yeah, so you can once again ask the participants if they have any questions. Otherwise, we can.
Participants, if you have any queries, you can please ask it. Sir, I think as of now, there are no more queries.
Okay, okay. Thank you, then. So,
Sir, on
thank you.
behalf of EACT Academy and Anandi ma'am, yes, of course, I will share the email ID. Sir, if you want, you can also share, sir.
Yeah. I'm sure. Yeah.
Thank you very much,
Yes,
sir.
sir.
On behalf of MNIT sir, and Department of Electronics and Communication Engineering, thank you very much, sir, for accepting our invitation. And thanks a lot, sir. The session was very much informative, especially the new technology that you are telling about the management of the electronics resources. And sir, it is very much important, sir. Thank you very much, sir.
Thank you, Swati. It was indeed a pleasure to be here on this platform, and it was really very nice to interact with you all and all the participants. Thank you, the wonderful audience. Yeah,
Thank
thank
you,
you.
sir. Dear participants, next session is from 11 a.m. You are requested to kindly please stay connected with us.